This is part one of the lecture Non-iterative and Iterative Image Reconstruction Methods. We'll be covering a least squares approach for backproject then filter reconstruction, looking at Tikhonov regularisation and then Gaussian maximum likelihood. So we're using a very simple reconstruction method in order to begin to unpack some other very key concepts in image reconstruction. So this is the simple method of BPF. We're modelling a back-projected PET image as just the true unknown distribution convolved with some point response function. And so I refer you to earlier videos to get a fuller understanding of that key convolution integral. By the convolution theorem, we can Fourier transform that and just turn it into a multiplication, which then gives rise to a very straightforward method for recovering the Fourier domain version of the object based on the back-projected image in the Fourier domain divided by the transfer function, where the transfer function is just the Fourier transform with a point spread function. And of course this is convolution, and so this is still requiring that this point response or point spread function be shift invariant. We will be looking at in subsequent parts of the lecture the case of shift variant responses for a more general matrix mapping. Okay, but let's just focus on the convolution case further to get further insight. So thanks to the convolution theorem then, we know that the Fourier domain description of the object, the object spectrum, just goes through a diagonal matrix T. In other words, it just gets point by point multiplied to deliver the Fourier transform of the back-projected image. That's just the forward model for the Fourier domain of the back-projected data. And so that matrix T, as mentioned, is diagonal, and it contains basically the Fourier transform of the point spread function. So if h of r is the point spread function from that previous slide, we just Fourier transform it. Obviously, we deal with this using the discrete Fourier transform in practice, and we just create a diagonal matrix, and down the diagonal there we just paste all of the values of the Fourier transform of the point response or point spread function, and then of course all the other elements are 0 to keep this as a diagonal matrix. And then just as an illustration here, I'm showing the modulation transfer function, which is basically a normalized version of that transfer function. And you can see that nearly always what's happening as we go to increasing spatial frequencies is that that blue line, the modulation transfer function, just shown here for 40 discrete spatial frequencies, starts high and generally decays downwards with increasing spatial frequency. So what that means is that the Fourier domain description, the spectrum of the object, basically is going through a kind of low-pass filter where there's an emphasis on the lower spatial frequencies and an attenuation, if you like, of the higher spatial frequencies. So that's why the back-projected image here in the Fourier domain manifests with higher spatial frequencies in the low end of the spectrum and loses some of the higher frequency details. And there's the inversion formula. Because T is diagonal, it's just so trivial to get that inverse. And you can see what effectively the inverse of T is. It's just going to be the reciprocal of those values. And I'm showing that here with that dotted line. And you can see that what happens is very significant. This is a log scale here, so this is not doing justice to the sheer range of values going on here. But it results in significant amplification of those, if you like, those diminished, those attenuated higher spatial frequencies, the kind of detail in the object. Those frequencies are getting significantly amplified. So you can view that very crudely as a form of high-pass filter. And then when we implement that, often we're using complex numbers in the Fourier domain. And so this is just f is equal to g, and then of course t minus 1 is just the inverse of those values, so I'm just showing that here, 1 over h, 1 over the transfer function. And then for practicality, we want to have real numbers in the denominator when we calculate this in MATLAB or Python, whatever it might be. And so we just multiply top and bottom by the complex conjugate and getting a real number on the denominator. Now, just to point out, of course, the reason I've called this slide motivation for least squares is that we've been assuming that this equality actually holds. But of course, we know that in reality we get, for example, measurement noise, and there's no reason at all to expect that equality to hold. There will be some noise in the back-projected image which transfers to noise in the Fourier domain. So G is noisy, and hopefully H is not noisy. If we've measured it, we could have had very high counts, so hopefully there's not much noise in H. But even then, we'll still be dealing with small values in this denominator, and so large amplification. And so any noise present in G could be notably amplified. But anyway, the point here is that we can't necessarily assume that equality to hold, and so we're going to take a least squares approach and just see what happens if we take that approach to solving this problem. And remember, we're always trying to find the object F, because if we can find the spectrum of the object F, we can just inverse Fourier transform it and get our reconstruction. Okay, an aside here briefly, and this is to simplify the description that follows. I'm going to be using, or rather assuming, only real values for the coefficients of the sines and cosines in the Fourier domain. Now, first of all, in emission tomography, like PET or SPECT, we only deal with real-valued objects anyway. And in fact, it was the real-valued sine and cosine transforms that Joseph Fourier himself originally used. And so I'm going to avoid complex numbers in the following description, and just show you the formula that I'll be using, which are perfectly valid for real-valued objects, such as the ones we're dealing with in emission tomography. So we're basically saying, in fact, this is just like a Fourier series, if you like, but just generalized to the case of non-periodic, aperiodic functions. So we're saying, this is just in 1D, that, for example, a radioactive concentration F as a function of position X is just given by a summation of cosine functions with particular amplitudes and a summation of sine functions of particular amplitudes. And there's basically a unique amplitude A and a unique amplitude B for each spatial frequency K. So you can see the spatial frequency K there for the cosine and there for the sine. So that's just a very simple summation of all of the spatial frequencies from minus infinity to plus infinity, all added together with different weighting factors to do a Fourier synthesis, which is what we get on the left-hand side here. And then, so that, if you like, that first line there was like a generalization of the Fourier series, or if you like, it's a sine and cosine version of the inverse Fourier transform, the Fourier synthesis. Here, I'm showing, if you like, the real version of the Fourier transform. This is like the Fourier analysis, but only using real numbers here. So we get the real coefficients for the cosine just by taking the function we wish to decompose, and multiplying it by the term for which we wish to find the coefficient. So if we want to find the coefficient for spatial frequency k, so that's a of k, then we just take that cos with that same k, multiply it by f of x, and integrate. And this just works by the beauty of orthogonality of the cosine functions. And so I refer you to other videos to understand that concept better, and the same goes for the sine. So I won't dwell much further on that, but just to say that I'll be therefore working with real values in the Fourier domain, in other words, assuming that my h's and f's and g's are all real valued. But of course, you can always implement this using conventional Fourier methods, which result to the complex number case again, and so I will incidentally show the formulae as well for when you use complex numbers, if you're using the FFT, for example. Okay, so back to where we were then, the motivation for the least squares approach for reconstruction. So what we're saying then is that G, so here I've just got a slight increase in the capitalization of G and F. Hopefully you can understand that, and that's not a problem for understanding. You can see now, instead of just G equals TF, I've just now added on the fact that there's going to be some random noise component in there due to measurement noise. And so therefore, instead of previously assuming G equals TF and just solving, now we're saying G equals TF plus some noise component, and then we could have as an objective the task of finding the spectrum F such that when we take the spectrum F and forward model it by applying the transfer function. In other words, it's just the convolution theorem. In other words, we're just multiplying by the Fourier transform of the point spread function. That's achieving a convolution, but looking at it in the Fourier domain, so it's just a product. So we need to find an F such that when it's modeled with the transfer function to predict a back-projected image in terms of the Fourier domain, it needs to match the back-projected image in the Fourier domain, which was G. So just find the F that minimizes that discrepancy. However, this description here is a bit naive because what could happen is that you could get negative errors, positive errors, and they could all cancel out, and yet F could be way off from what it needs to be. So that's one possible motivation, but we'll get to a better one, a statistical one later on when we look at Gaussians. But that's a good motivation for saying, let's not just naively look at the differences, let's look at the square difference. That way every discrepancy will always have a positive value and contribution to our counting of the total error. Okay, so that allows us to define this least squares cost function or loss function or objective function, whatever your preferred notation is. I guess I'm using L for loss here. And so you can see it's basically the same, saying find the F, which when you forward model it by using the transfer function needs to match the spectrum of the back projected image. So we're trying to find the spectrum of the object F. Transfer function needs to match the spectrum of the back projected image, such that if we do that a comparison between the measured G and our forward modeled version of our reconstruction in the Fourier domain, we need that discrepancy to be as small as possible, and now we're squaring every discrepancy, so whether this model is too big or too small relative to G, it will still have a net contribution to this overall square error, if you like. And so that's why we're looking for a least square error, if you like, a least squares solution. Okay, so a quick aside again, just for, I'm sure you know this already, but just in case, just talking about L2 norms because they're used a lot. So if we've got a vector A, then the L2 norm is just saying, well, look at every single element, take the magnitude, square the magnitudes, and then take the square root. So this is like, you can view it as just finding the magnitude, the length, the size of a vector. Think of it in terms of Pythagoras, a right-angled triangle, you know, a squared plus b squared equals c squared, and then you just square root to get the hypotenuse. You can think of it in that way, in a kind of Euclidean sense, if you like. Because I'm pointing this out because it's obviously related to that least squares cost function or loss function that I just mentioned. But in fact, just for your information, again, I'm sure you know, but we can define what's called an LP norm, where now we sum, again, still the magnitudes of the coefficients, or rather the elements of the vector A, but now we can raise them to a power of p, and then when we've done the summation, we can do 1 over p. So therefore, L2 norm is obviously sum of squares and then square root, but you could do L3, you could do L1. L1 is a common example where you're just basically adding up the absolute values in the vector. L0 is like just counting the number of non-zero elements, and L infinite, I think, is just the largest value, the largest element in the vector. So there are extreme cases, but anyway, it's probably L1, L2, L0 are the ones that you're probably going to need to know the most. Okay, so back again to our least squares problem, we can now rewrite it like this and say, well, the spectrum of the object F, which is the least squares solution, would be the F, the argument F, that minimizes that discrepancy vector. Okay, so the L2 norm squared, because obviously the L2 norm already has the square root in here, and we're doing a least squares problem, so we do need to have a square in there. We just want to minimize that discrepancy, minimize the size of that error vector, if you like, in this L2 sense. Okay, so let's go ahead and do that. It's obviously going to be quite straightforward, but it's good to build up to where we're headed with more general methodology. So first of all, then we're going to take the partial derivative, because notice that there are j equals 1 to capital J parameters. That's as many elements as there are in the Fourier domain description of the reconstructed image F that we're trying to find. So there are capital J values or parameters that we're trying to find. So we're going to take the partial derivative of that loss function with respect to just one of the parameters. So this sums over capital J, and we're just going to pick out one of them, an arbitrary one of those J's, and we're going to label it as frequency index n. Okay, so there's the partial derivative of the loss function. Just to note, of course, that all of the terms here are effectively constant with regard to the partial derivative, except for the case where j equals n. Okay, so when j equals n, then that's now got f of n present, and so we can do the derivative. It's not constant, so we actually need to calculate the derivative. So the 2 comes down the front, gn minus hn fn. By the chain rule, then we just multiply by the derivative of this. And so again, with respect to fn, that's just going to be minus hn. So to get the minimum, the extremum of that function, this is still a function of fn at this point, but we want to set it to 0 in order to find the minimum of that loss function, that cost function. So the moment I set that to 0, again, this is another reason for doing this simple case, is to point out important notation. The moment I set that to 0, I now label fn, because that's now going to be a fixed value of fn that solves this. I now label that with ls to show that it's the least squares estimate. And, well, we can see where this is going. It's not a very exciting solution, but at least we now know that that very same formula that we've been using beforehand, just by simplistic use of the convolution theorem, happens to also be the least squares solution. Perhaps it's not a great surprise, even in the presence of noisy data. So in other words, that noise basically gets included with G, and you just have to just take that noise and go ahead and invert anyway. In other words, just take the noisy G and divide by H. As mentioned, this has all been assuming real values in the Fourier domain, but if we were to have done the more complex version of it, then we would have, or rather, let me put it this way, if we deal with this in the case of complex values in the Fourier domain, then from a practical perspective, it's useful to have a real number in the denominator here, which means just multiply top and bottom by the complex conjugate of Hn, and then this is real, and then we can work with that more readily as just a straightforward complex number for subsequent inverse discrete Fourier transform. Okay, so that's the least squares solution. Just to show you then what it does, I mean, it's the same as the direct inversion case without assuming, we're assumed equality. It's the same solution. If we don't have noise, then if this is a back-projected image from a brain phantom, quite a sort of low-resolution brain phantom for the sake of simplicity here, if we have noise-free data, then we get a fairly good reconstruction. The reason this is maybe not as good as it should be is that the back-projected point spread functions effectively are spreading over the entire space. And so that means if we're just doing a point spread function that's located, say, in the middle of the phantom, and then we're only getting its tails going out, say, minus 40 to plus 40, whereas over here, the point spread function should have tails that go all the way out at least by a distance of 80 pixels. So there's a lot of that could be said there, but just to say that assuming a shift invariant PSF is not quite the case with this level of edge effect. Anyway, it's still a fairly good reconstruction because this was all done in the Fourier domain, and so it's not going to be perfect due to the replicates in the discrete Fourier domain. If, however, we add noise, or rather if we back project noisy data, so this is like correlated Poisson noise, if you like, here in the back projection, if we just do that naive direct inversion, then our reconstruction will be something like, this is just a representative figure because it's very unspectacular, it will look something like this, or probably even worse, where it'd be largely black with maybe just some spike of some high value. In other words, there is a huge problem, and the errors in the process just become too severe if you do a direct inversion of noisy data. So that's going to motivate us to look at regularisation methods, as well as, by the way, downstream, more accurate least squares methods where we don't have these kind of edge issues with the PSF, because strictly this is effectively a shift variant problem.